Welcome back to the hyperbolic heaping chamber. We are back once again to stack many things upon many things to create large piles of things, for which we have affectionately named heaps. Good progress is being made. We had a shorter session yesterday, but hoping to recoup the losses today. Fridays are generally just shorter days because there's a lot going on. But fortunately, we're in the weekend and there's ample time. I didn't wake up as early as I'd like to, but I guess that's kind of what I get for working East Coast time and staying up late West Coast time. At the same time, I've been getting caught up in reading some good books, and sometimes it's just hard to put the pages down. That being the case, if you see someone doing what I just did, you're going to put your hand on their shoulder and you're going to shake them. And you're going to say, stop it, and get some help. Because that's what we need. Because, yeah, I end up staying up late sometimes reading these books, and it's just not a good way to make things sustainable. That being the case, actually I have to check real quick. Yeah, so that being the case, we have a comment today from a legendary human being, part-time entrepreneur, full-time visionary, full-time good person, and received I guess it's true. Thomas has been here for a long time. Feel strong, man. Also, make sure to check out Thomas Wong Coding. He is a legend. The whole channel basically is us trying to get on Thomas's level. Also, there are tons of people in Discord who are absolutely cooking LeetCode who we are trying to catch up to as well. But the distance will be covered. He says, this is why C++ or Java is the best, because it has inbuilt data structures, heap for the win. What else can be said? It is true. It is true. I'm seeing why people are using Python and Java. They're all built in. Also, C++ has a very vast data structure library, and I think it has a ton of different variations too. But they forgot to mention that TypeScript is a joy to use. So, yeah, it is tough. It is tough. I really wish they'd give us some basic data structures, but it's a web language and they never intended to. So that kind of sucks, to be honest. But maybe since we're learning them by hand, we'll gain something. I'm sure there's some secret sauce to be had in the implementation that will serve us for the future. And that's what I'm hoping for. So maybe that's copium, and it probably could be. So I'm not really certain. That being the case, though, the plan going forward, we're still working through the Heap Explore card. Also, we've kind of just been slashing through easies. I think we might have awakened, but after we do this heap card, we're gonna have to keep slashing through. I've also been realizing we're almost halfway through all the easies, so what's important to say is that when we finish the easies, we'd like to have grasped a lot of the fundamental underlying concepts of things. And while I'm still reading Siena, I have been for like 200 days now, or more like, I don't even know, maybe like 150 days. I just read it before I go to bed. And it's pretty good at getting me to sleep. So we don't make a ton of progress, we make some progress somehow. That being the case, I'd like to have some fundamentals down. And that's when I realized it was probably important for us to do this heap thing so that we can just generalize our programming model in our head. Maybe we'll remember more. I remember a study, I think it was, or maybe it was from a book. I think it was called, I think it was John Whiteskin's book. But basically, if you took a chess grandmaster and a chess novice, and you gave them, and you had a chessboard in front of you, you could arrange the pieces into a randomly ordered set on the table. And you would give them 5 seconds to look at the board, right? And then you destroy the board basically, and you'd ask them to recreate all the positions as the pieces were on the board. And obviously the grandmasters could reconstruct the board in 5 seconds. I mean, they knew the board through and through. The novices, however, could maybe only get 3 pieces, and then the other remaining pieces they couldn't actually put on the board properly. But then they did something different. The way they had arranged the pieces the first time was in, a natural game setting. White pieces on one side, black on the other side. All the places the pieces were in were valid positions that could be reached from their starting positions. The second time they did the test, they put the pieces in random spots. I mean, creating positions that aren't possible, right? In just really odd combinations that you just never see in a game, even in thousands of games that Grandmasters have played. And what happened is they weren't any better at recollecting the board than the novices in this scenario. What that says that I think there's a way that pattern recognition through all the games they have played bolsters their memory, so they can recall games they've watched one time, or they can recreate games and positions or specific sections in games off the top of their heads. Because I think underneath all this brain garbage nonsense is some very strong pattern-based recognition system that helps us compress memory or something like that. All this to say, bring it all the way back to the heap. Learning the implementation could be helpful for more pattern recognition and just helping us remember more problems, which I probably could have TLDR'd. So that being the case, the goal for today is continue through the Explore card. I have a Geeks for Geeks tab open because I took a look at how a heap is actually supposed to be implemented, and it seems like it can be done with an array. I didn't read too much into it, but it looks like the underlying data structure is an array. So I used a tree, which made it way more complicated. That being the case, we're going to continue through the Explore card. We're going to find another heap problem, and I'm going to try again and implement the heap from scratch, except this time with an array as the underlying data structure. And that's the goal for today. And at the same time, if this is something that interests you, or you're also doing LeetCode, or you feel like, you have some tips and tricks. I just received a message from someone in Discord who is going to give me some tips on heaps. So if that's something you're interested in, you should definitely join the Hyperbolic Heaping Chamber, a chamber designed to master the knowledge of heaps. And then once you're through with that, that'll be the end of it. So I think all that being said, I should probably jump into the session. We're going to do a standard hour banger and get to work. So here we are. The Explore card has returned. This is where we were. When we discussed selection sort, the basic principle involved. When did they discuss selection sort? When we discussed selection sort, the basic principle involved finding the minimum element and moving it to the front. We repeated this continuously until we sorted the entire list. But this is the Heap Explore card. Algorithm for bottom-up heapification of input into the heap. So we're creating a max heap. We'll probably want to do the swap as long as an element is greater than, if an element is less than its children, if an element is less than its children, we definitely want to swap it with its greater element. Two cases for a node. It is greater than its left child. It's greater than its left child and right child. In this case, it's doing good, right? In this case, proceeds to the next node when indexed before the current array index. 2. There exists a child node that is greater than the current node. Right. Wait, no. The max heap, the node children must be children. It must, for a node, it must be greater than its children. Right. There's another case where there exists a child node that is greater than the current node, which would break the rule. In this case, swap the current node with the child node. This fixes a violation of the max heap property. Repeat the process with the node. Repeat the process with the node until the max heap property is no longer violated. Repeat step 2 on every node in the binary tree. Key property of this method is that by processing the nodes from the bottom up, once we are at a specific node in our heap, it is guaranteed that all child nodes node in our heap, it is guaranteed that all child nodes are also heaps. Yes, but that makes heap sort better than selection, so does the running time of the algorithm is now n log n. Here we go. Well, there's no one talking in this video. Right, 1 has no children, so we go to 8. 8 has no children, so we go to 9. 10 has no children, so we go to 6. 6 has no children, so we go to 5. Is any of 5's children greater than 5? It is. Is greater. Wait a second. They kept going. First step is to bottom up heapify the unordered array. You have 3. 3 has a child, a left child of 8. If we check that child, both 8 and 6 are greater than 3, so we can take the largest child. 8 and 3. Then we still have where we are at, so we can check, does 3 have any children which are greater than 3? And we do, so we start with 5. Then we swap it. Wait a sec. Oh. Then the second thing we do is swap A0 with the max element with A, which would be heaps. Swap A sub 0, which is the max element. This is true. With A sub heap size minus 1, which would be 1. Heap the max element. Then we heapify the whole thing again. If we heapify the whole thing again, the only thing we end up, 3 has no children, 7 has no children, 2 has no children, 6 has no children. We go to 5. 5 has a child, but it's greater than 3. We go to 1. 1 has a child which is greater than it, so we swap it with 7. And then 8 is fine, and so is 9. Then we move 9 into the end. Then we remove 9 from the heap. Right, then we heapify again. Going down, 1 has no children, 2 has no children, 3 has no children, 5 has no children. 7 is greater than both of its children. Then we had 3. 3 was not greater than both of its children, so we swapped it with 6. I think I see how you can implement this heap with a array. So 3 has no children, 5 has no children, 2 has no children, 6 is greater than both of its elements, and we're fine. Now we need to swap. Oh, yeah. Then we get to 1, and 1 is greater. I mean, 1 has a child, its left child, it's greater than itself. Then we get to swap it with 5 or 3, but we choose 5. Then we can swap 6 with the last element, which is 3, and then remove 6 from the heap. This was right. This is just heap sort is really interesting. Isn't heap sort just the manual implementation of a heap? Does it each time after you run max heapify? heapify operation takes n log n time, doesn't it? Right, in-place heapification is a linear time operation. I'm sure I see. Then the heapify operation they're talking about on the heap explorer card, they must be talking about that operation. Interesting. Use the heap data structure to obtain K's largest or smallest elements. Top K's largest or smallest elements. Solution of the top K largest elements. Construct the max heap. Add all elements into the max heap. Heapify it.
In this video, we'll look at how to use the heap to solve a top K problem. For top K, there are two.
Another video.
In this video, we'll look at how to use the heap to solve a top K problem. For top K, there are two subproblems. The first is the problem of top K largest, the second is the problem of top K smallest. Top K largest means getting the top K largest elements. Top K smallest means getting the top K smallest elements. First, let's look at top K largest. Here are some numbers. We want to take out the two largest elements. Note that this is the largest. Since we're going to take the two largest elements, we're definitely going to need a max heap. First, we have to convert these numbers into a complete binary tree. Then heapify the complete binary tree into a max heap. So, how do we heapify it? First of all, we can ignore the leaf node here, can't we? Because it doesn't have to exchange with its children. And then we consider this node. We're going to compare it with its children. And then we find that there is a child larger than it. So all we have to do is exchange it with its largest child. After exchanging, we consider this 4. In this subtree, it is in the right positions, so let's look above. For this node, this 2 is smaller than both left and right child nodes. Now we're going to exchange the 2 with the biggest child. After we've moved 2 into this position, now we can see that this 2 is in the right place. It is smaller than its parent node and bigger than its children. At this moment, we consider the whole tree and see that it's still a complete binary tree. At the same time, it satisfies the properties of a max heap, so we've heapified it into a new max heap. After we get this new max heap, we know that our top element is the largest among all the elements in the max heap. Now we remove the top element. In order to delete 4, the top element, we need to set the value of the last element to the top element and then delete the last node. When I delete 4, at this point, this tree is still a complete binary tree, but it does not satisfy the properties of a max heap. So we're going to compare 0 to its children, and we find that 0 is smaller than both its children. So we'll exchange 0 with 0 of a this new max heap, we know that our top element is the largest among all elements in the max heap. Now we remove the top element. In order to delete 4, the top element, we need to set the value of the last element to the top element and then delete the last node. When I delete 4, at this point, this tree is still a complete binary tree, but it does not satisfy the properties of a max heap. So we're going to compare 0 to its children, and we find that 0 is smaller than both its children. So we'll exchange 0 with its largest child. After we exchange 0 and 3, looking at this complete binary tree, it satisfies the properties of a max heap. Now we have a new max heap. We have our largest number, 4, and in this new max heap, we can get our next largest element, 3. And there you have the two largest elements. Isn't that right? We now have taken out the top k largest elements. Next, let's talk about the top k smallest elements. We have the same numbers, but now we need to take out the smallest 2 elements. Here, we want to convert those numbers into a complete binary tree. And then we'll heapify it. What will we heapify to, the max heap or the min heap? Since we're going to take the smallest 2 elements of a min heap, its top elements are the smallest in the entire collection. So here we're going to heapify into a min heap. How do we perform the heapify operation for a min heap? Here, we first look at the leaves. We don't need to worry about them because they don't have child nodes, so we can't exchange them. Next, we want to consider this node. We can see that one of its children is smaller than it. All we have to do is exchange them, and now we're in this new position. You can see that this subtree already satisfies the properties of the min heap. Let's go to the layer above. We find that there is a child that is smaller than it. Because it is a min heap, so we're going to exchange it with its smallest child. After this exchange, consider this 2 here. It still has a child that is smaller than it. All we have to do at this point is to exchange them. After this, you can see this tree is a complete binary tree, and also satisfies the property of a min heap. So we have a new min heap.
I just realized the timer is not showing.
The top element of the min heap is the smallest element. If we take out the 0, it is the smallest element, isn't it? Next we will delete the 0. If we are going to delete the 0, we need to move the last element to the top, and then delete the last node. To satisfy the properties of a complete binary tree, I'm going to compare 2 to its left and right child, to find that the left child is smaller than it. This time all we have to do is exchange it with its smallest child node. After the exchange, 2 is in the right position, and then we have a new min heap. When I have this new min heap, I also have the next smallest value, which is the top element in the heap. Now, we've taken out the top 2 smallest elements. What is the time complexity for the top k largest and top k smallest? Here, no matter.
Time complexity. Well, it takes linear time to load the heap, or to heapify the heap. Worst case, we want to know the top n elements, so I'm thinking n log n plus, no, is it n plus n log n? Oh no, deletion takes log of n. Yeah, we might do it n times, so I would say n to heapify plus n log n plus k. Oh no, it would be n to heapify and then k log k to remove them.
Whether it's top k largest or top k smallest, they both start with a heapify operation, which is a time complexity of big O of n. Then we have a process of deleting and getting the top element. Because we're going to get k elements, and it's the smallest or largest k elements, every delete operation is log of n. In the process of deleting and getting the top k elements, our time complexity is O k log of n. In this process, we have these two time complexities. We then have to use the maximum time complexity. So its total time complexity should be k log n. Its space complexity is O of n, because no matter whether it is a top k largest or smallest, these two problems both use an extra heap, a max heap and a min heap respectively. So its space complexity is O of n.
K log n. Because we're going to do k deletion operations, but there's a max of n numbers. I see. How is this better than just? I guess that would be better. Right. K log n. K log n or n log n.
In this video, let's take a look at the second solution of the top k problem. The problem we're trying to solve here is still top k largest and smallest. First, let's take a look at how top k largest can be solved by the second solution. In the last video, we showed you how to use the max heap to find the top k largest elements. In this video, we're using the min heap to solve this problem. We are still using the previous example. We also have the same questions as before, that is, to find the two largest elements. In this second solution, we'll be using a min heap. We start by making the size of the min heap equal to k, which is 2 here. And then we take these elements and add them to the min heap one by one. First, let's add 2. We've only added one element to the min heap, so the heap's largest current value is 2. This means we can still add elements to it. We'll add 1 to the heap. Once you add it in, you'll find 1 is our smallest element in the min heap, so 1 should be our top element. Then we can add 3. But when we added 3 to the heap, we find that the min heap already has 2 elements at this time. The heap is full. All we have to do is compare 3 to the current top elements. If 3 is larger than the top element, that means 3 could be one of the top k largest values. All I have to do is delete the top element, then add in 3. After 3 is added, at this point, you can see that in the min heap, there are only 2 elements. You see, for the first 3 numbers, the 2 elements that I have in the min heap are the top 2 largest of the first 3 elements. After adding the 3, we're going to add the 4 in. When we're adding 4, we find that the min heap is full again. What we're going to do is the same as before. Compare 4 with the top element. In the min heap, the top element is the smallest one, so its top element is 2 at this point. We find that 4 is bigger than 2, so all we have to do is delete 2 and add 4. When we add 0 to the min heap, we find that the heap is full again. We're going to compare the top element with the 0 and check which one is larger. At this point, you find that the top element is larger, so we can ignore 0 at this point. There's no need to add it to the heap, because it's smaller than the min heap's top element. After we've added all the elements, there are 2 elements left in the min heap, and you can see that these 2 elements are actually the top 2 largest elements among our original numbers. So we can take these 2 elements out of the min heap, which will be our final result. In this example, what is the time complexity? Since there are only 2 elements in the min heap, in other words, there are only k elements, each time an element is added, its time complexity is log of k. But we have to add in elements n times, so its time complexity is big O of n log k. this is the time complexity. For space complexity, since we limit the size of the heap to k, the space complexity is big O of k. Now let's look at the solution for the top k smallest element. In the last video, we were using a min heap to solve the top k smallest problem. In this video, we're going to solve it using a max heap. The idea is basically the same as before. First, we have to have a max heap. We make the size of the heap equal to k, which in this example is equal to 2. The same value in our previous example. Then what we're going to do is add elements one by one to the max heap. First, we add 2. After 2 is added, there is only one element in the max heap, so we can still add one more element. Then let's add 1 to the heap. Once we add it in, the heap will be full. If we're going to add a 3, what we have to do is compare the top elements with 3. For this max heap, its top element is the largest element in the heap, so its top element is 2. We're going to compare 3 and 2 and check which is smaller. Whichever is smaller remains in the max heap. The reason being, we're looking for the top k smallest elements. So in this heap, we're trying to keep elements small. Because 3 is bigger than 2, we can throw away 3. It can't be in the max heap, so then we move to the next number. We want to add 4, but since 4 is bigger than 2, we also ignore 4. You don't have to add it to the max heap. And finally, for this 0, we compare this 0 with this 2. We find that the 0 is smaller than 2. Since 0 is smaller than 2, it could be one of the top k smallest values. So we're going to delete this 2 and add 0. So we have 2 elements in the max heap. These 2 elements, if you take a look, you'll find that they are the smallest 2 elements among our first 5 numbers. And that's how we solve the top k smallest problem. We take out the 2 elements in our max heap, and we have our final values. For this solution, what is the time complexity? Since the max heap holds k elements, when each element is added, its time complexity is log of k. But since we have to add elements in n times, its time complexity is big O of n log k. This is its time complexity. For space complexity, since we're maintaining k elements, its overall space complexity is big O of k. This is the second solution for our top k smallest element.
I don't understand at all.
We're going to add the 4 in. When we're adding 4, we find that the min heap is full again. What we're going to do is the same as before. Compare 4 with the top element. In the min heap, the top element is the smallest one, so its top element is 2 at this point. We find that 4 is bigger than 2, so all we have to do is delete 2 and add 4. When we add 0 to the min heap, we find that the heap is full again. We're going to compare the top element with the 0 and check which one is larger. At this point, we find that the top element is larger, so we can ignore 0 at this point. There's no need to add it to the heap, because it's smaller than the min heap's top element. After we've added all the elements, there are 2 elements left in the min heap, and you can see that these 2 elements are actually the top 2 largest elements among our original numbers. So we can take these 2 elements out of the min heap, which will be our final result. In this example, what is the time complexity? Since there are only 2 elements in the min heap, in other words, there are only k elements, Each time an element is added, its time complexity is log of k. But we have to add in elements n times, so its time complexity is big O of n log k. This is the time complexity. For space complexity, since we limit the size of the heap to k, the space complexity is big O of k. Now let's look at the solution for the top k smallest element. In the last video, we were using a min heap to solve the top k smallest problem. In this video, we're going to solve it using a max heap. The idea is basically the same as before. First, we have to have a max heap. We make the size of the heap equal to k, which in this example is equal to 2. The same value in our previous example. Then what we're going to do is add elements one by one to the max heap. First, we add 2. After 2 is added, there is only one element in the max heap, so we can still add one more element. Then let's add 1 to the heap. Once we add it in, the heap will be full. If we're going to add a 3, what we have to do is compare the top elements with 3. For this max heap, its top element is the largest element in the heap, so its top element is 2. We're going to compare 3 and 2 and check which is smaller. Whichever is smaller remains in the max heap. The reason being, we're looking for the top k smallest elements. So in this heap, we're trying to keep elements small. Because 3 is bigger than 2, we can throw away 3. It can't be in the max heap, so then we move to the next number. We want to add 4, but since 4 is bigger than 2, we also ignore 4. You don't have to add it to the max heap. And finally, for this 0, we compare this 0 with this 2. We find that the 0 is smaller than 2. Since 0 is smaller than 2, it could be one of the top k smallest values. So we're going to delete this 2 and add 0. So we have 2 elements in the max heap. These 2 elements, if you take a look, you'll find that they are the smallest 2 elements among our first 5 numbers. And that's how we solve the top k smallest problem. We take out the 2 elements in our max heap, and we have our final values. For this solution, what is the time complexity? Since the max heap holds k elements, when each element is added, its time complexity is log of k. But since we have to add elements in n times, its time complexity is big O of n log k. This is its time complexity. For space complexity, since we're maintaining k elements, its overall space complexity is big O of k. This is the second solution for our top k smallest elements.
Okay, those videos have burned me out crazy. At least tomorrow we can jump into these problems below. We have quite a long list to do. I think we'll stop there for today.